Hello and welcome to this tutorial. So we're going to go through a few questions in preparation for the physiology test 2 that will be coming up in the next couple of weeks or next few days if you will. Okay, so without further ado, let's just get right into it. So we have a few questions that we're going to be tackling. So feel free to pause the video and write down what you think is the answer. Then I'll be going through each of those options. And so this is a true or false kind of question scenario, and then yes, let's answer it and tackle it that way. All right. So question number one says coronary blood flow to the left ventricle increases during A. Early siso, and B. Myocardial hypoxia, C. Hypothermia, D. Stimulation of sympathetic nerves to the heart, and then E. Arterial hypertension. Okay, so you can pause the video and uh, go through here. All right, so let's go through each of the options. Option number one says that it increases during during early cycle. Okay, is that true? Is that false? Okay, so for this one, it is actually false. It's a false statement. Let me just write it properly. Okay, so that option is false. Why is it false? It's generally because during early cycle, as the heart is contracting, what basically happens is that coronary blood flow is reduced. Why is that so? It's because the high blood pressure actually closes off uh, uh, the blood that will be going to the heart. So coronary blood flow, that's the key word, coronary blood flow. That means the blood that is flowing to the tissues of the heart, to the lung tissues, uh, to the heart walls themselves. That's what we're terming coronary blood flow. And then specifically to the left ventricle. Okay, so for the left ventricle, it's going to have to go through a series of veins that's better described in anatomy. But here, our focus is what happens to those coronary blood vessels during early cycle. So early cycle, so this is just a period at the onset of contraction. Okay, at the onset of contraction, cysto is contraction. Okay, usually when we just say cysto, it refers to ventricular contraction. Yes, so in this case, if the ventricles are contracting, the early stage of that contraction, you're going to have these coronary blood vessels actually being closed because of the high pressure of the blood that is being pumped to the myocardium, or that is being pumped out of the heart. All right, so I hope that is clear enough. So the blood vessels are going to close up, so it's going to cause reduced blood flow to the coronary arteries that leads to the left ventricle. Simply because the pressure is too high. So it's like the pressure is high and then it closes off. Instead of opening the blood vessels, it closes off. So when the during, let's say, let's say, so when the pressure has abated a bit, when the pressure has gone down a bit, those vessels are now able to let blood flow into the coronary uh, vessel spaces. Okay, that said, option B says during myocardial hypoxia, blood flow to the left ventricle will increase during myocardial hypoxia. Okay, so two words here, myocardial and then hypoxia. We know that hypoxia is having insufficiency of oxygen reaching a particular tissue. Then in this case, we are saying that the particular tissue of interest is the myocardium itself. So in the myocardium, if you have hypoxia, does blood flow to the left ventricle? Does blood flow to that ventricle or the heart? Because the left ventricle is part of the myocardium. So does blood flow then increase to those areas? This is actually true because wherever you're going to have hypoxia, the body is going to try to compensate by sending a lot of blood to that area. That is general for a lot of other tissues. Okay, not only the myocardium, but also for every other tissue in the body. When you find that it is being hypoxic, is under hypoxic conditions, there's less oxygen. The body is going to try to send a lot of blood there so that they can be uh, ample nutrients and ample oxygen being exchanged due to uh, sending a lot of blood to that area. So that is also true for that. And then during hypothermia, coronary blood flow to the left ventricle increases during hypothermia. Is that true or is that false? That one looks false to me. Okay, the reason why it's false is because during hypothermia, the body systems generally slow down. So even coronary blood flow itself is going to slow down. Okay, hypothermia slows down almost every metabolic activity. So even the heart metabolic activities during hypothermia, it's going to reduce. What is hypothermia? That's having a lower than average, a lower than normal body temperature. Okay, that's what we are terming as hypothermia. So during that case, during that situation, you're going to have reduce coronary blood flow to the left ventricle and every other part of the heart itself. And this stimulation of sympathetic nerves to the heart. Okay, stimulation of sympathetic nerves to the heart. Does coronary blood flow increase when you stimulate the sympathetic nerves to the heart? Okay, is that true? Is that false? That is actually true to me. Okay, that is true. The reason why it's true is because look at this. So we'll start from what does stimulation of sympathetic nerves that are going to the heart, what does it do to the heart actually? So sympathetic innervation to the heart actually speeds up the rate of beating of the heart, and also that it ultimately increases the cardiac output. So the heart is working harder. After the heart is working harder, you expect that there is a lot of metabolic activities happening in the myocardium itself. So when that is happening, of course, you're going to need a lot of oxygen to compensate, because those are tissues. The myocardium contains muscle tissue, and that muscle tissue, of course, needs oxygen. So if it's doing a lot of work, of course, it's going to require a lot of oxygen. So that is true. And then the last option for this question is saying during arterial hypertension. During arterial hypertension, does blood flow to the left ventricle increase during arterial hypertension? This is also true. So there's a direct relationship between hypertension, arterial hypertension. That arterial hypertension, what this simply means is that you have increased blood pressure in the arteries. So if you have increased blood pressure in the arteries, peripheral arteries, by the way, once the blood has left the aortas into the arteries and everything, uh, blood flow to the left ventricle also increase as a result of that. So there's a direct relationship between coronary blood flow to the left ventricle, not only to the left ventricle but to other parts of the myocardium. Uh, that is directly related to the arterial hypertension. Okay, can move on to the next question. Um, Second question says local metabolic activity is the chief factor determining the rate of blood flow to the A, the heart, B, the skin, C, the skeletal muscle, D, the lung, then E, the kidney. Okay, so let's try to understand the question first of all. Local metabolic activity is the chief factor determining the rate of blood flow to the. So we are saying that, as I'm from saying, I did mention when we are talking about stimulation of sympathetic nerves to the heart that once you increase the metabolic activity of a particular organ, what you're going to have is that that organ, of course, is going to require a lot more oxygen. Okay, so then how does the body transport oxygen to a particular organ? It sends it through the blood. So that then will increase the amount of blood being sent to a particular organ. But then, what organs in what organs does this occur? That's what the question is asking here. So in the heart, for example, I've already said that that is true. So this one will quickly go over. In the skin, okay, I have a problem with the skin. This one is false. The reason why is because local metabolic activity in the uh, skin is not very sufficient to call uh, uh, blood flow, to call a lot of blood flow. The main reason why there is a lot of blood flow to the skin at a particular point, or there is less blood flow. It's just for uh, control, homeostasis, for control of temperature, basically, not metabolism. Because the main cells that you have in there are the keratinocytes, the melanocytes, and just a few macrophages here. So uh, there's not really a lot of metabolic activities that cause for blood to be sent to that particular organ, unless you tell me that the skin does a lot of work. What work does it do? It's just an epithelia, it's covering, it's doing its thing, but that thing that it does is not a lot of metabolic work. I hope that makes sense. That's not a lot of metabolic work, and then that does not call for a lot of blood. So the rate of blood flow in the skin is rather controlled by uh, temperature. So if you need to release some heat to the skin, then vasodilation, skin vessels that are close to the skin, of course, and then the heat is going to be released that way. And if it's cold, of course, vasoconstriction. So the rate of blood flow is determined by a factor that is not metabolic in the skin. Then for skeletal muscle, it's quite obvious. Muscles do a lot of work, and then since that is the case, a lot of metabolic activity there as well. That is very true. Similar to the heart because it's also a muscle, so basically the same thing. To the lungs, I also have a problem with this. Okay, one thing I'm going to tell you about the lungs is that the lungs will always receive the same amount of blood flow regardless, because even if you don't want to send blood uh, to the lungs, you have to, just because there is gaseous sections that has to occur. So this one is false, because the rate of blood flow to the lungs is not determined by the metabolic activity in the lung, but rather it's because oxygen has to be diffused into the blood at all times. So always the concentration, the rate of flow of blood is going to be determined by uh, how much the body needs. The whole body actually needs oxygen. So it's fairly constant. The amount of blood that is sent to the lungs is fairly constant at each particular time, because the body will still require oxygen at any particular time. You're still going to have to oxygenate the blood. So a large amount of blood is actually has to be passed through the lungs, whether the lungs are actually in a metabolic state or not. Okay, so this is false, because this does not depend on the metabolic activity of the liver. Whether the liver is metabolically active or not, you still have to send blood there for gaseous exchange. Okay, then the kidney. The kidney serves a similar function as well. The blood has to be filtered regardless. Okay, regardless whether the kidney is being in a metabolic state or not. So blood still has to be sent there for filtration. So that as well cannot be a reason to say that the rate of blood flow is controlled by metabolic activities, local metabolic activity. The key word there is local metabolic activity. This means is that the metabolic activity that is happening in that particular tissue, not for any other reason, but for that particular metabolic activities of the cells of that particular organ that we are talking about. So that is not true as well. That is false, because the kidney will receive uh, the blood flow that is supposed to receive just because it has to filter it, not because it's being metabolically active. All right. And then thirdly, it's another question. The pressure A drop across large veins is similar to that along large arteries. So since these are long statements, I'll read them each as we say whether they're true or false. So remember how I said to read true or false questions? You read the question here and then you continue it with the option. So the pressure drop along large veins is similar to that along large arteries. Is that true? Is that false? You can pause the video, and then so the answer actually there, question number 3, option A, is true. So the pressure drop across large veins is similar to that across large arteries. What does this mean? Is that if you take the length, okay, let's say from the abdominal aorta, from the thoracic aorta that is descending down from the descending aorta, of course. So the descending aorta, if you just take it as it is, coming down uh, where it bifurcates into the left and right common iliac arteries. So we are saying that the pressure drop, because obviously because this part is closer to the heart, the arch of the aorta here, and it's coming from the left ventricle of the heart there. So as blood is coming here, of course, it's going to be under high pressure here, and then as it goes down here, the pressure is going to be reducing because of the distance it is from the heart itself. So if you take this as the heart somewhere there, once it pumps blood like that, you're going to find that the blood is going to be under high pressure as it is leaving, but then by the time it's getting here, the pressure is low. So this is being likened to similar blood vessels, like maybe the inferior vena cava that is coming alongside here, coming to insert into the right atrium, like the inferior vena cava, as well as a large vein. So large vein and large arteries, they're being compared here. Is they're saying that is the pressure drop across, like the way it's dropping from top to bottom, is it the same like uh, along another large vein like the inferior vena cava itself? Okay, so that is true. Why am I saying that? The simple and most basic answer that you can give for this is that large veins and large arteries do not have any resistance. So usually the pressure drop is usually brought about due to whether the blood vessels there are resistant or not. So if the blood vessels are not resistant, then the pressure drop is not going to be great. Sorry, the pressure drop is going to be very great because there's nothing to oppose. Remember that the blood pressure is simply how the force with which blood is pushing against the vascular walls. So if the vascular walls are providing resistance, then that means they are resisting the flow of blood. If they are resisting the flow of blood by maybe vasoconstricting, then that means that that blood that is in those vessels is going to be pushing against a smaller lumen, and then the pressure is going to increase like that. So the pressure drop will be is inversely proportional to uh, to the lumen, or rather the uh, let's say there's a word that I had used, the resistance. Yes, it's there is inversely proportional to the resistance. If you have high resistance, the pressure drop will be won't be very great. Okay, if you have high resistance, then the pressure drop will be very low. But if you have uh, no resistance at all, then the pressure drop will be very high, because obviously there's going to be quick flow um, of blood from that area where there is higher pressure to that area where there is no resistance at all. So there's no pressure that the blood is going to be pushing against. There's no resistance that the blood is going to be pushing against. Okay. All right. So that is the reason why, because large veins and large arteries actually have uh, similar figures of resistance. They are both raw. Um, uh, they are both wrong candidates. Okay, they are both wrong candidates for uh, resistance. In other words, what I'm trying to say is that these large veins and large arteries have very low resistance. So very low. Oh my God, very low resistance. Yeah, terrible thing to say those words in that particular order. But yeah, option B, the pressure drop. So the pressure drop across the hepatic portal bed is similar to that across the splenic vascular bed. So remember, if you go to a bit of anatomy, it's going to tell you that there is a hepatic portal bed and a splenic vascular bed. So these are just the splenic vessels that drain into the hepatic portal bed, and then the hepatic portal bed is going to drain into the river, the the liver parenchyma, and then that is going to drop into uh, the hepatic vein. The hepatic vein is going to drop into the vena cava, okay, the inferior vena cava. So for blood to flow in that manner, there has to be a pressure drop. Okay, that means one of these vessels has to be uh, non-resistant. It doesn't have to be very resistant, because if it is very resistant, then blood is not going to flow, especially those Let's say, for example, like we have said that we have like splenic capillaries leading into the uh, hepatic veins, and the hepatic veins going into the liver. After they go into the liver is the hepatic vein, then going into joining the inferior vena cava like that. So for blood to flow this direction, that means the pressure that is here, okay, the pressure that is here has to be high, and then the resistance has to be low, so that the resistance of these blood vessels that is flowing into it has to be very low, so that the blood can now move in that direction. So if the resistance is very low, remember that I said that the resistance is inversely proportional to the pressure. So that means if we say that there is very low resistance in this area, that means uh, the pressure drop as well uh, is very high. So that means if a pressure drop is high, what we simply mean is how is it different from where it started. So if the pressure drop is high, that means it's the pressure is starting high where it's starting from here. So point one, that's where the pressure is starting from. It's very high, and then here where it's ending, point number two, is very low. So it's creating that pressure gradient that is very steep, so to say. Look at it like a gradient. If the resistance is very low where you're going, that means the pressure gradient is going to be very steep, and then blood is going to be flowing in that direction, in that manner. That's how blood flows in the veins, because of pressure drops in different capillary beds. So the capillary beds that the blood is coming from needs to have higher pressure than where it's going. Okay, higher pressure, and then these ones also, where it's going in a capillary bed that is going, or another vessel that is going in, also has to have little resistance, so that the blood can easily flow into that particular capillary bed, or the venules and the different vessels, that so that the blood can be flowing in that direction. So if you check, that's why the blood vessels will become bigger as you are entering the heart, as well as you are coming from the heart and to the heart. Okay, that's just to aid in pressure gradients. Okay, so that it maintains the pressure. I don't know if you get what I mean. So the blood vessels will be getting thicker as you are will be getting bigger as you're getting closer to the heart, so that it creates pressure gradients. Pressure gradients, if you check that out, you find that it's actually coincides. Okay. All right. So option C says that the pressure in the hepatic portal vein exceeds that in the inferior vena cava. If you check, the hepatic portal vein is the one that is here. Okay. So we have the splenic capillaries here, somewhere in the intestine. Then here you have the hepatic portal vein that is now taking the blood to the liver. Then the inferior vena cava is all the way up here. So like I said, for this system to work, for the blood flow to flow in this system, that means the pressure in the vessels that are at point A, where you're coming from to where you're going, these ones where you're coming from, the pressure needs to be high. Okay, the pressure needs to be high. So here it's saying that the hepatic portal vein exceeds that in the inferior vena cava. If the one in the hepatic portal vein is exceeding and this one is lower, then that means it's going to be flow from a place of higher pressure to a place of lower pressure, and that is actually what happens. So that is true, because blood actually flows from a place of higher pressure, that is the hepatic portal vein, into the liver, and then obviously towards the inferior vena cava that has actually much lower blood pressure. Okay, I hope that is clear so far. Okay, so that is true. Like I said, it's true. I write it properly. Okay, so we can move on to the next option. So the pressure drop across the vascular bed, or option D, the pressure drop across the vascular bed in the foot is greater when the subject is in the vertical than when he is in the horizontal position. Okay, so that is actually false. Okay, that is actually false. Okay, so the reason why that one is false The reason why the pressure drop across the vascular bed in the foot is greater when the subject is in the vertical than when he is in the, actually marked it wrong, then he is the horizontal position. So this is comparing arterial and vascular. So although the arterial is not really mentioned here, it's actually comparing against uh, the vascular. So it's saying the pressure drop across the vascular bed, because wherever you find the vascular bed, there is also a capillary bed. So across the vascular bed in the foot is greater when the person is in the vertical than when he is in the horizontal position. So the true part of this statement is that pressure will increase when the subject is in the vertical than when he's in the horizontal position. The vertical position basically standing, vertical position basically standing, but then horizontal position that's maybe laying down. So when you're standing up, obviously the pressure drop, okay, the pressure drop is going to be similar for both the vascular and the arterial. So the vascular won't be greater. So that's where this statement is wrong, because it's comparing against the arterial vascular bed um, and the venous vascular bed as well. Okay. Yes. So it's not only the vascular uh, bed. So pardon my mix of words there. So vascular bed simply just means the capillary bed, the vascular bed, capillary bed, and yeah. So when you're standing, not only the vascular bed that will be in the foot will be affected. Okay, so the vascular bed across the entire body will actually be affected when you're in the vertical position or the lying down position. Okay, so the vascular bed, not only the vascular bed in the foot, but the entire arterial and venous blood pressures the pressure drops will be greater in a vertical position than when you're in a horizontal position. So if there's anything to take away from this particular question is that the pressure drop is similar throughout the vessels of the body, no matter the location. It's greater when you're standing or in a vertical position than when you are lying or in a horizontal position. That's what we're basically saying. So when you are standing up, the pressure drop across not only the vascular bed in the foot but also in the entire body is going to be greater than when you are. Yes, I hope that is okay. So the problem there is that it was saying the vascular bed in the foot. That's allow me to make that correction. The vascular bed in the foot. Okay, but actually the vascular bed throughout the body, all the arteries and veins in the body are affected. The pressure drop will be greater in the entire body when a person is in the vertical position than when he's in a vertical position. That's what we are saying. All right. Last option E. It says the pressure in the foot veins is lower when walking than when standing still. Okay, so this option uh, is actually true. Okay, so for the last option, the option is true. Why? It basically has to do with muscle pump. Okay, muscle pump. The muscles help in pumping blood back to uh, back to the inferior vena cava and ultimately back to the heart. So the pressure drop or the pressure in the foot when you're walking is going to be lower than when you're standing still. One of the things to SWAT. Remember physiology, guys. SWAT your MCQs and EMQs, or yeah, your true or false. SWAT them, guys, because they just bring the same things. They might bring it true this time. Maybe remember what I said last time. Maybe this time they might tell you that um, in the foot veins is lower when standing still. than when walking. That means they've just swapped walking and standing still. And that shouldn't get you confused because you know where uh, the truth lies. All right, question number 4. Hope I can be done in quick time. Question number 4. The second heart sound differs from the first heart sound in that it is. Okay, we've now gone to heart sound. So this tutorial was basically mostly dealing with a lot of just dealing with a lot of CVS, and then added just GIT, maybe 2 questions at the end. Yes, so number 4, the second heart sound differs from the first heart sound in that it is A, related to turbulence set by valve closure. Okay, A, is it related to the turbulence set by valve closure? Yes, that is true. But is that why it's different from the first? So we are comparing the first heart sound and the second heart sound. So if we say that the second heart sound is related to turbulence set by valve closure, that means we are saying that that does not happen in the first heart sound. So please understand the question in that manner. The second heart sound differs from the first heart sound in that it is A, related to turbulence set by valve closure. So this is not true. The reason why it's not true, it's not that it's not related to heart uh, valve closure, but it's because both of them are related to valve closure. The first one is related to closure of the atrioventricular valves, and then the second heart sound is related to closure of the semi-lunar valves. So both of them are related to valve closure. So that is not the difference between the second and the first. So the one that we are comparing against the other with is the second heart sound. So the second heart sound differs from the first heart sound in that, and I actually wrote true. So let me correct that quickly. So this one is false. False because both of them are actually uh, so it's the same. They tell you that tell us the differences between the first and the second heart sound, and then you say that they are caused by turbulence set up by valve closure. That's not a difference because that's a similarity. Okay. Yes. So if I ask you maybe what is similar about the first and second heart sound, is that they are both related to valve closure. But then which valves? The first one is the closure of the atrioventricular valves, and then the second one is for closure of the semi-lunar valves. All right. Then B, it is longer lasting than the first sound. Longer lasting than the first sound. Is that true? Is that false? That is actually false because it is actually shorter. The second one is actually shorter. So this is the one that we are comparing the other again. So the second heart sound differs from the first in that it is. So this it is referring to the first one, the first, which is the second heart sound. So it's referring to this. So yes, I'm sure you. I know you guys did English, so you understand what the question is actually saying. So it is longer than the first sound. So the first sound is actually longer than the second one. So that option is false because the option is saying the second one is the one that is longer. So makes it false. So first one longer, second one shorter. Is it higher in frequency? That one is true. That option is true. The second one is higher in frequency. It's shorter than the first one, but it's higher in frequency. Okay, it's higher in frequency. If you check the frequency ranges, you might be given frequency ranges, yes, but just know that it's higher in frequency. They will probably never ask you to know the frequency, the actual frequency, but just know that one is higher in frequency than the other. And which one is higher than the other? The first one is lower in frequency, second one is higher in frequency. So the second heart sound is higher in frequency than the first one. That's one difference among the two. So then D is saying it's like occasionally split, occasionally split. That option is false because both of them can be split. Why can they be split, or what is actually causing this splitting in the sound? So splitting in sound basically means we are not having one sound. So where you're supposed to hear one heart sound, you hear two. That means two or more, but usually it's just two. So that is usually a problem that is caused by asynchronous uh, valve closure. What do we mean? Valve closure, maybe that particular valve. Okay, remember that a valve has, if it's the bicuspid, it has two valves. It has two flaps. The valve has two flaps, and then if it's the semilunar valves, they are, and the semilunar valves and the tricuspid valve has three flaps. So those flaps can be misaligned in the case where maybe the other one, if it's a um, or let's say a tricuspid, maybe two of them close earlier, or the flaps go up earlier than the others, the other one, then that means it's going to be a synchronous valve closure. That means the valve does not close at one particular time. And also another source of asynchronous valve closure is that when the ventricles contract, you have two semilunar valves. Semilunar valve, one in the opening to the aorta and one in the opening to the pulmonary circulation, the pulmonary artery. One in the pulmonary artery, one in the aorta. So we call that the aortic valve and the the semilunar valve, pulmonary circuit, pulmonary yes, going to the pulmonary circulation. So that, remember that when blood the blood is being ejected to this thing, it happens at the same time. Both ventricles contract at the same time. They're supposed to contract at the same time, and then when they contract at the same time, it's only the atria and the vessels that and the ventricles that don't contract at the same time. You don't have the atria and the ventricles contracting at the same time, but the atria themselves, the two of them, will contract at the same time, and then the ventricles themselves will contract also at the same time, just a bit later. The reason why is because you need to allow a bit of time for ventricular infilling, of course. Yes, so since you have two valves, one going to the aorta and one going to the pulmonary, those two valves can be closing at a slightly different time as well. So that can also cause it to be occasionally split. The second heart sound can be occasionally split because these two valves are not closing at the exact same time. One is closing faster than the other, and then that will cause a split sound because uh, this sound we're only supposed to hear one. Okay, one, maybe it's a, is it a lab dub sound? Maybe the dub part, you're not supposed to hear two sounds. You're supposed to hear one, but because these valves are closing asynchronously, that means they're not in synchrony, or they're not synchronizing in uh, the way they're closing. Then that means they're going to have two sounds, one from the other and one from the other. So both of them can actually, this can actually happen for both the first and the second heart valve, because the first and second heart sound, because the first sound, remember, is for the atrioventricular valve. We also have two atrioventricular valves, so those ones can also be beating at different times. So both of them can actually be split in certain pathological conditions. So that's not a difference, because both of them can be split. It's actually a similarity. So E is saying it's heard when the ventricles are relaxing. Ventricular relaxation is actually that is actually true, because uh, um, second heart sound, remember we said that it is due to closure of the semilunar valves. When the semilunar valves are contracting, then that means the ventricles are relaxing. Uh, when the semilunar valves are closing, rather, that means the ventricles have relaxed, and then blood is entering the ventricles, but then the blood that is entering the ventricles is only coming from the atria, and then the valves that are closing off the aorta and the pulmonary circulation are preventing blood from coming back. So when the ventricles, so if you take the heart like this, ventricular septum here, and then you have another septum like this. Let me use another color for the blood. Show you exactly what I mean. So if blood enters here, let's call this part the atria, and then this is the pulmonary pulmonary artery. So if blood goes, if the ventricles are relaxing, this part, the ventricles are relaxing, then that means blood is being drawn into the ventricles. If the ventricles are contracting, then blood is being pushed out of the ventricle. So if the ventricles are relaxing, blood is coming into the ventricles. So, but blood will want to come in from both the pulmonary and the vena cava here, or the atria. It's going to want to come from the atria and the pulmonary artery there. Or is it the pulmonary vein? It's the pulmonary artery. Yeah, sorry. So yeah, pulmonary artery. So what prevents blood from actually flowing backwards here? So if blood is actually being pulled from here, it's going to flow backwards. So the semilunar valves are going to close here to prevent the blood from flowing backwards. So if the um, the second, we say that the second heart valve is the heart sound is actually caused by closure of this valve. So if this valve is closing, then obviously you have the ventricles relaxing, because then the reason why you're closing this is to prevent the blood flowing back into this ventricle. So that means the ventricle is relaxed. If blood can flow into the ventricle, then the ventricle is definitely relaxed. Okay, move on to question 5. Question 5 says pulmonary vascular resistance is A, less than one third that offered by the systemic circuit. That statement is true. It's because pulmonary vascular resistance is very low. The reason why it's very low is because the lungs need to aerate a large amount of, of blood. They need to offer a large surface for gaseous exchange. So that means a lot of blood has to pass through it. So the vascular resistance in the pulmonary uh, circuit is very low compared to that offered by the systemic circuit. So it's just less than one third that offered by the systemic circuit. Hope that makes sense. Then B, decreased when the alveolar oxygen pressure falls. Decreased when the alveolar pressure so this one we said it was true, and the alveolar oxygen pressure falls. So that is false because a decreased alveolar oxygen pressure actually causes uh, pulmonary vascular resistance is decreased. It actually causes an increase in pulmonary vascular resistance. Okay, so just one thing to spot as well is that pulmonary vascular resistance, the resistance in the uh, pulmonary circulation is going to be increased when the oxygen pressure falls. So it's another inverse relationship between the partial pressure of oxygen and uh, the the pressure, or rather the pulmonary vascular resistance. So pulmonary vascular resistance and oxygen partial pressure in the alveoli inversely proportional. Okay, so option C says expressed in units of volume of flow per unit per time per unit measure gradient. So I don't even know if they can ask you this question, but they're just asking about the units. But these are not the actual units for these are the units for conductance and not for pulmonary vascular resistance. So this is not the actual unit, but I think don't worry about this. They're not going to ask you about units anyway. Okay, D on question 5, we have decreased during exercise. Okay, pulmonary vascular resistance is decreased during exercise. Okay, is that true or is that false? So from if you're trying to reason, let's just use reasoning. If you're exercising, you need a lot of oxygen. A lot of oxygen. How do you get a lot of oxygen? Of course, you send a lot of blood to the lungs so that that large amount of blood can pick a large amount of oxygen, and then it can take that large amount of oxygen to the rest of the circulation, the rest of the body. Sorry. So for that to happen, remember that pulmonary vascular resistance or vascular resistance in an area where you need blood flow to be a lot of, you have to reduce it. Because if there is a lot of resistance, that means obviously the blood is not going to flow into that area. So that area is basically resisting. If you have a lot of resistance in that particular area, that means you are resisting the blood flow in that area. So in the lungs, for example, for a person who is exercising, during exercising, and you need a lot of uh, oxygen, of course you have to reduce the pulmonary vascular resistance. So D option is actually true because you have to reduce pulmonary resistance. The pulmonary resistance is reduced. So this happens automatically, but the pulmonary resistance is reduced during exercise. That is true. And E, regulation, regulated reflexly by sympathetic vasoconstrictor nerves. So that is false. Okay, so it is false. So it is false because pulmonary vascular resistance, it is um, regulated by local factors rather than nervous input. So pulmonary vascular resistance, you have to swatter that it is not regulated by local uh, local or CNS input, but rather it's regulated by local activities. Okay, local activities like if uh, there's large blood flow. Okay, so if the blood flow, if the lungs themselves notice that there's a large amount of blood that is being sent to this uh, particular area to the lungs, then that means it reduces the resistance so that it can help compensate like that. All right, going to question 6. In the heart, the left atrial wall is about 3 times thicker than the right atrial wall. Is that true? Is that false? That option is false. Why? Because it's kind of like a trick question. We know that the left ventricle is about 3 times thicker than the right ventricle, but it's not the atria. The atria, both of the atria in the left and in the right, they are the same size. But for the ventricles, this would have been true if we had for the ventricles. But since it is for the atria, it is false. Okay, question option B. The systolic contraction normally begins in the left atrium. Okay, systolic contraction does not begin in the left atrium. It actually begins in the right atrium at the sinoatrial node. The sinoatrial node is in the right atrium. So that's what makes this false. So in the heart, excitation spreads directly from atrial muscle cells to ventricular muscle cells. Okay, so this is in saying that the muscles in the atria are directly connected to the muscles that are in the ventricles, and then once an excitation in the atria reaches those muscle cells there, is able to transfer into the muscle cells of the ventricular muscle fibers. That does not happen like that because excitation spreads through special fibers, special conducting fibers. Okay, those you have left bundle branch, you have right bundle branch. Those uh, interventricular branches, atrioventricular branches, all of those. So the ones that are responsible for taking blood from, sorry, an impulse from the uh, left atria, right atria, and down into the left and right ventricles as well. So from the atria to the ventricles, you have bundle branches that is taking the impulse, not through a direct connection between these cells. Okay, hope that is okay. So that is also false. All right. Option D. Atrial and ventricular muscle contracts simultaneously in siso. Okay, atrial and ventricular muscle contracts simultaneously in siso. Simultaneously means at the same time during contraction. So that is false because obviously the atria have to contract first so that they can push blood into the ventricles. So for the ventricles to receive the blood, they have to be relaxed. So then they will contract so that they push the blood out through the pulmonary artery, of course, and the aorta. All right. So that makes this option false as well because they do not contract simultaneously, they contract asynchronically. Okay, that means at different times, not at the same time. E, the contracting ventricles shorten from apex to base. Apex to base. So if you look at the heart, has this shape like that. Then it's calling. This is not the shape of heart. It looks like a mango. Okay, so it has the heart has uh pointy end here like that. So this is what is called the apex, and then at the back there you're having what is known as the base. So at the apex, that's where you have the ventricles, true ventricles, you have the interventricular septum here, and then you have two atria there. So as it contracts, basically the arrangement of the muscles in the heart is so much so that when it contracts, especially when the ventricles contract, you're going to have it like the muscles kind of like go up. Okay, so if you just Google, maybe just go on YouTube and look for an animation of a beating heart, you're going to see that as it is contracting from the ventricles, it's more like going up. So once it, this part from the apex is like going up to the base. So that's what this statement is saying. The contracting ventricles shorten from apex to base. That is true. So please look up an animation of the heart beating. You find that what I'm saying here is actually the case. At the apex, which is this area, it's going to be shortening, and then not really shortening, but it's going to be like moving towards the base. The heart will be like moving towards the base, which is there. So that is what is being described in this statement. So that is the true statement in this case. All right, so move on to question number 7. The absolute refractory period in the ventricles, absolute refractory period. Remember what an absolute refractory period is. A, it is the period when the ventricles are completely inexcitable. That to me sounds true because if I remember very well, on muscle physiology, we talked about the um, the refractory period as a period where you are not able to elicit another action potential because you are from exciting that particular tissue. So in this case, the ventricles, remember, their muscles as well being excited, and then um, you're going to have a part known as absolute refractory period. There's relative and absolute. So absolute refractory period is the period when the ventricles are completely inexcitable. That's true. True for any muscle actually. Completely inexcitable. Then B corresponds to the period of ventricular depolarization. Corresponds to the corresponds to the approximately to the period of ventricular depolarization. That is true. This is true because um the absolute refractory period in the ventricles is when the ventricles have been depolarized. So if you have depolarized the ventricles, then that means you cannot actually uh, excite them again. So if you have depolarized a muscle, a nerve, whatever, that means you are not able to excite it again because it is just from being depolarized. So that's what we are saying corresponds to the period of ventricular depolarization. If the muscles are depolarized, you cannot not actually excite them again. Then C corresponds approximately to the period of ventricular contraction. So what follows depolarization? Action potential. What follows action potential? It is actually a contraction of the muscle. If this action potential is occurring in a muscle, so in this case, we are saying it's in the ventricle. So if the depolarization has occurred in the ventricular muscles, that means depolarization in the ventricular muscles simply means the muscles is about to contract. So that's what they are approximately simply means. So it's that period when it's being depolarized, it's the period in which there's ventricular contraction as well. So that is also true. And then D, it is shorter than the corresponding period in atrial muscle. So it's basically the same. It's not really shorter. It's basically the same, if not longer. All right. And then E decreases during sympathetic stimulation of the heart. Okay, this is true. The reason why it's true is because the absolute refractory period refers to a period where you cannot excite the muscle, the heart muscle, right? But during sympathetic stimulation, you want the heart to beat faster. Sympathetics, fight or flight, you want the heart beats faster. If the heart is beating faster, that means you have to reduce the period in which the heart is not excitable. So in that absolute refractory period, you have to reduce it so that you can be able to excite your heart. Uh, you're able to excite your heart and make it beat faster in that particular manner. All right, so that is true. I actually said I wrote true here instead of false. All right, so false. All right, question number 8, which is the second to the last question. Second from the last question. Carbon dioxide is carried in the blood, A, in combination with the hemoglobin molecule. Does that occur? Yes, it occurs. That is true. In combination with plasma protein, does that occur? Of course, it does occur. Does it, uh, is it in physical solution in plasma? Of course, that is also true. Then D, it's greater quantity in red blood cells than in plasma. Okay, this one is false. Why? It's because the greater quantity is actually in bicarbonate form, and bicarbonate is in the plasma, and then in the red blood cells you have the hemoglobin molecule. So it is greater in quantity in the plasma than in the red blood cells because it is greater in the HCO or the bicarbonate ion rather than uh, in the hemoglobin molecule. Oxygen is the one that is carried as per hemoglobin molecule in the highest order or the highest concentration. But for carbon dioxide, it's mainly dissolved in the plasma as a bicarbonate ion, mainly as the bicarbonate ion. And so that makes E true as well because that's what I'm just from saying. So question 9, shall move on to question 9. Appetite for food is lost when A, certain hypothalamic centers, certain hypothalamic areas are stimulated. So this is true because in the hypothalamus, that's why you have both hunger and let me just write this correctly. So you have hunger and satiety areas both in the hypothalamus. So the hypothalamus, in other words, has areas that control hunger and also satiety. Satiety means being full. So it controls when you are full and it also controls when you are hungry. So what does this entail? This entails that if uh, certain areas a- uh, in the hypothalamic area, or yes, in the hypothalamus, are stimulated, and if that area happens to be the hunger centers, then if it happens to be the satiety centers rather, then it's going to be game over for you. So you have both hunger and satiety. So if certain hypothalamic areas happens to be uh, the satiety areas that are stimulated, then that means you're going to have loss of appetite because you're going to feel full. Then B, certain hypothalamic areas are destroyed. Let's say if you destroy the hunger areas. So remember that we had the satiety and the hunger areas. So if you destroy the hunger areas, then that means you're not going to feel hungry because you no longer have receptors to tell you that you're actually hungry. So you're not going to have appetite for food. Then C, so this one is true as well. Then C, the stomach is distended. All right, so C is actually true. The stomach being distended actually means you have had something in your stomach. What that tells the the brain is that no, there's something in your stomach, so then stop eating anything else. So it makes you lose appetite for food. That's the reason why when you are full, you kind of lose appetite for anything else because the body is just trying to prevent you from overeating. So that is actually true as well. And then D, the stomach is surgically removed. So if the stomach is surgically removed, does the appetite for food get lost? So appetite for food is lost when the stomach is surgically removed. That is false because if you remove the stomach does not play a role in you. What can I say? Does not really play a role. Hunger does not depend on the stomach being there or not. Okay, but being full does actually depend on the stomach being distended or not because it has stretchy receptors. Okay, so but hunger itself does not depend on the stomach being there or not. So even if you get a gastrectomy or gastrectomy, something like that, means if they remove your stomach, you're still going to feel hungry because whether the stomach is there or not, you're still going to feel hungry. So yes, so the hunger does not really depend whether you have a stomach or not. Even if you don't have a stomach, if it's removed surgically, that actually happens. So those people are actually going to be eating very small amount of food at very spaced intervals because once the food reaches the stomach, there it has very little space, very little things going on in there, and then it goes directly into the intestine. They're not able to hold food, in other words. So the way they take in food is a little bit different. Small chunks at very spaced intervals, and then yeah, life goes on like that. Like person maybe is constantly eating, but they're eating small amounts of food over a prolonged period of time. Prolonged intervals of time. Okay, that's what we are saying. So the stomach is, if the stomach is surgically removed, you are still not going to lose appetite. Still going to feel hungry. And E, blood glucose falls. Does your appetite for food, is it lost when the blood glucose falls? Actually, the blood glucose, if it falls, is actually supposed to increase your hunger levels. So the appetite for food increases when blood glucose falls. It's not lost. So this option is false as well. All right, we have come to the end of a few questions that I prepared for this particular tutorial. Expect more, and yes, so this file shall be uploaded to our drive as usual, and it has the key for what we are just from discussing, so that you can go through quickly and just get one or two things as you're revising. Otherwise, for me, I'm signing out. Thank you.